Welcome to a brief dissertation about the eclipsing binary star UZ4, as observed by the South African Astronomical Observatory in January 2014. We will examine a set of 15 FITS files, taken by the 1.9-meter refractor telescope at SAAO, using the SHOCK CCD camera. Without further ado, let's briefly examine the SAAO observatory first. The South African Astronomical Observatory, SAAO, is located in the area of Sutherland, South Africa. Under an average sky background flux of 22 magnitudes per arcsecond squared, it is blessed by an exceptional dark sky for astronomical observations. The SAAO, in fact, has long been at the forefront of astronomical research, utilizing cutting-edge technology to capture and analyze the wonders of the universe. The 4 SHOCK cameras are each optimized for a specific type of observation. The first, SHOCK 1, is a high-speed photometer that can capture up to 50 frames per second, allowing it to track the rapid changes in brightness of variable stars and other fast-evolving phenomena. The second, SHOCK 2, is a high-speed imager that can capture up to 25 frames per second, making it ideal for capturing the rapidly changing details of solar system objects like asteroids and comets. The third instrument, SHOCK 3, is a multi-channel camera that can capture high-resolution images in 3 different wavelengths simultaneously. This makes it ideal for studying the detailed structure and evolution of star-forming regions, supernova remnants, and other complex phenomena. Finally, SHOCK 4 is a high-resolution imager that can capture images with exceptional detail and sensitivity, making it ideal for studying faint objects like distant galaxies and quasars. In this table, you can see the fields of view related to the 1.9-meter telescope in conjunction with the SHOCK cameras. Now it is time to talk about our target, UZ Fornacis. Shown here in the optical image, retrieved from Aladdin, plate solved in Astro Image J, UZ4, is a variable star, located in the constellation Fornacis, also referred to as a cataclysmic variable, due to the large increase of brightness that renders these types of objects sometimes visible to the naked eye. The appearance of such a new light in the sky gave them also the name of novae, new, in Latin. Variability in brightness can be caused by several physical factors, including the normal pulsating of energy release by a star. But in the case of UZ4, a white dwarf, the variability is caused by its orbiting companion, an M-class dwarf, that transits through our line of sight. UZ4 is a very faint object, G magnitude of 16.637, as shown in Simbad. With the parallax method, the Gaia mission determined the distance of this system as 240 parsecs. Remember, 1 parsec is equal to 3.26 light-years. It is quite possible that the white dwarf is devouring matter from its orbiting companion, and it is a fascinating and equally horrifying thought that at least 2 planets have been found, engaged in their deadly dance in the cosmos, orbiting the 2 central stars, as we can check from the NASA Exoplanet Archive. The aforementioned NASA Exoplanet Archive shows 2 confirmed exoplanets in the UZ4 system. However, the referred paper, Potter et al. 2011, gives the detection of 2 giant extrasolar planets, orbiting the eclipsing polar, UZ Fornacis, only as possible. The cited paper gives a sound and accurate method to calculate the orbital periods of this system, P-bin, which is stated as 0.087865425 days, or 126.526 minutes. The study of UZ Fornacis continued, with the improvement of technology, and several other papers have been issued. A brief search in the Astrophysics Data System, ADS, yields other and more recent studies, the most recent being shown in this slide. Now we can proceed with our own study, based on the 15 FITS files that we have been given. These are the 15 FITS files, provided by SAAO. As we can see from the header, opened in Astro Image J, the observations have been conducted with a V-band filter, at a wavelength of 550 nanometers. The date of the observation is the 12th of January 2014. As mentioned, this study is conducted with the use of Astro Image J, a Java-based powerful image processing and photometric software developed by Karen Collins, and presented in a paper in 2017. The files provided are raw, therefore our photometric analysis will not be so accurate. In Astro Image J, we open the first FITS file. We adjust the sky background to better visualize the object of our interest, keeping in mind that these adjustments have no effect whatsoever to the file itself. Clicking on the table icon in the astronomy window, the file header will be shown. We take note of the object's coordinates, the epoch, the date of the observation, the time UTC of the observation, and the heliocentric Julian date, or HJD. We now zoom in the object, and if we move the cursor to the center of the object, we can notice, in the upper boxes, the pixel coordinates, FITS X and FITS Y. Then we depress Alt-click in order to see the best apertures, according to Astro Image J. We can notice that the software decided for a source aperture radius of 11 pixels, and a sky annulus that starts from 19 pixels and ends at 28 pixels. We can now save those apertures for analysis, and we depress the single aperture button in the Astro Image J main window. We then click over the object and a measurements table will appear, showing all the relevant data that we need. If we open the next FITS file and do the same procedure, we notice that Astro Image J shows us a different aperture there. This happens for various reasons: a slight change of the conditions during the observation, but more importantly, because of the intrinsic variability of the object we are studying. This variation in apertures will yield another set of measurements that the software automatically places below the previous analysis. By doing the same procedure for all the rest of the FITS files, we can notice how Astro Image J has chosen very different apertures for each image. It was also important for us to take note of the pixel coordinates of the object's center, so to give the software a correct indication on where to perform its analysis, especially for the image taken at UTC time 2100 hours, 6 minutes and 39 seconds, where we can see how faint the object became in such a short time, since the time at which the observation started was UTC 2000 hours, 40 minutes and 16 seconds. After importing a sequence of all the 15 FITS files, Astro Image J can show us an animation where we can notice how the object's luminosity changes during the time span of the observation related to these files. Although Astro Image J has the ability to suggest the apertures that best fit to the object, we can proceed manually and change those apertures to record the different readings and see which is the minimum size of aperture that contains all the possible star counts. We do this for the first 3 FITS files, examining the star counts and how the sky background counts change as the sky annulus changes. We require the minimum possible aperture for the star counts, because a larger aperture would contaminate the analysis of the software with readings that do not belong in the studied object. Therefore, the idea is to adjust the inner circle so that it is as close as possible to the boundaries of the star. We can set a source aperture radius where the fitted line of the source counts intercepts the horizontal fit line from the sky. In this particular case, an aperture of 8 would do. In this example, with the first FITS file, with a source aperture of 8, we can see that reducing the aperture any further is not a good idea, because some of the information would be lost. We apply the same concepts to the other subsequent 2 FITS files, and find that an aperture of 8 is indeed a good compromise. Likewise, we change the apertures of the sky annuli, and measure the variations. To do this, we concentrate on the first FITS file, and we proceed to change the annulus inner and outer radii, recording the results on a table. As we can see, the change in the sky counts per pixel is not so dramatic, leading to think that we can stay reasonably confident with Astro Image J's suggestion for the sky. Having decided to set our source apertures at 8, and to leave the sky annuli apertures at 19 and 28, as suggested by Astro Image J, we proceed with the analysis of all the 15 FITS files, using the Aperture Photometry tool in the software, and consequently produce a table that we process in Excel. We just need to use some care to click at exactly the pixel coordinates in the center of the object. As for this, the images appear sufficiently aligned, as we saw in the earlier short video. The resulting table is shown in the next slide. Here is the table elaborated in Excel. We have calculated the instrumental magnitude, assuming an arbitrary offset as 0, because we do not have any other reference non-saturated star in this particular set of images. Therefore, we used Pogson's equation, as shown in this slide, to determine an instrumental magnitude, along with the error that is calculated according to Hainaut et al. 2005. The resulting graph clearly shows the rapid dip in brightness of the object, of about 3 magnitudes, during the fast transit of the M-class dwarf star, in front of the white dwarf. A dip in brightness that lasted only about 19 minutes. Referring to the aforementioned paper by Stephen Potter, we can now assess the number of orbital periods that have elapsed since a known time t0, as shown in the slide. A brief examination on the British Astronomical Association's website yields a date of our 0 point as the 3rd of February 2005. Therefore, the median point of our star's dip happened almost 9 years later than our 0 point. We can use the equation shown to calculate the number n of orbital periods, yielding this result, which, divided by 9 years, means more than 4,000 orbital periods, or about 11 per day. However, because the n result is a non-integer, it is clear that our readings of the dip from the graph are not accurate, as we can see by the large error bars at the time of the minimum. To get better results, we should get more readings, more observations, and surely, perform calibration with appropriate dark frames, flat fields, and bias frames. A multi-wavelength study is also essential to refine our results. In any case, as reported in the most recent studies by Z. N. Carngale and Potter, it is possible that one of the sources of errors are generated by the gravitational influences of the 2 planets orbiting the system, and 2 cyclic variations of about 5.17 and 14.76 years have been found, as shown in their paper, dated 2019. This concludes our presentation. Thank you so much for watching.